In this video, I will be proving proposition 10 and proposition 26 from Euclid's propositions. Okay, so proposition 10 says to bisect a segment. And what this means is that we are given some segment AB, and we need to show that there is some point M such that M is between A and B, and AM is congruent to MB. So what that looks like is that we're given this segment AB, and we want to find a point M such that AM is congruent to MB. That's our goal. And to do that, what we're going to do is, given this segment AB, we're going to construct two equilateral triangles. And we're going to do this because this is going to allow us to prove that different triangles from the resulting equilateral triangles are congruent. And then we can use SAS to prove that these two segments are congruent. Okay, so what we need to do is we need to construct those triangles. And the way we do this is we are going to take this radius length AB, and we're going to rotate it around. And when these two resulting parts of the circle hit, those are going to be equilateral triangles because all of these distances have radius AB. And we're going to do this on the bottom side as well. Not the cleanest, but that'll do. And we're going to name these points C and C prime. Okay, and I want to clean this up just a little bit, so I have this picture down here. Okay, so we have these two equilateral triangles. So let's just label what we know real quick. We have that AC is congruent to BC, which is congruent to AB, which in turn is also congruent to AC prime and C prime B. Right, that's all from our construction that we just did. Okay, now what we want to do is I want to actually split these things in half. So I want to construct CC prime. Right, so we're going to construct CC prime, and we can do that by I1. And what we want to do is we want to prove that two of these smaller triangles are congruent to one another, therefore splitting these two segments apart evenly. Okay, so things that we have right now, we have triangles. Now we have triangle ACC prime and triangle BCC prime. And we know that these are congruent to one another by SSS. Because AC is congruent to CB, BC prime is congruent to AC prime, and then CC prime is congruent to itself. Right? So if we just write that down, we have AC congruent to BC. We have AC prime congruent to BC prime. And then we have CC prime congruent to itself. And then these are congruent. These two triangles are congruent by SSS. Okay, now, because those are congruent by SSS, we know that, and I want to back up just a second. We know that ACC, triangle ACC prime, and triangle BCC prime is isosceles. Because they have these lengths congruent to one another, right? AC is congruent to AC prime, therefore that triangle ACC prime is isosceles. Similarly for the triangle BCC prime. Okay, so that means we know that this angle is congruent to this angle, right? So angle AC prime C is congruent to angle ACC prime. And we also know that angle BCC prime is congruent to angle BC prime C. Okay, and that's based off of the definition and other propositions based off of isosceles triangles. Okay, so isosceles triangles will have base angles congruent. Okay, so we have those two things. And because, and we can go further with this, because those two bigger triangles are congruent by SSS, we also know that angle AC C prime is congruent to BCC prime. So not only are they congruent to its other base angle, they're actually congruent to each other, right? So we no longer need that double marking. Those angles in that teal color, those are all going to be congruent. All right, so this angle is congruent to this angle, and this angle is congruent to this angle. Okay, now, the last part. This line, and I probably should have done this before, this line, CC prime, intersects AB at the point that we're going to call M. Okay, so now we can actually identify two smaller triangles. So now we're going to focus on triangle ACM and triangle BCM. And you should be able to tell those triangles are congruent because of SAS. Where CM is congruent to itself, angle MCA, or I guess C prime CA, or ACC prime, I'll try and be consistent, is congruent to C prime or BCC prime. And then we have that angle, that segment AC is congruent to segment BC. Now, because of all of this, because those two triangles are congruent, their corresponding sides are congruent. Specifically, AM is congruent to BM. And then we have a segment bisector. Okay, so that proves proposition 8. Okay, the second proposition I want to prove is proposition 26, and there are two parts to this. First, proposition 26 says angle side angle congruence and angle angle side congruence. So there are two parts to this. There's ASA and then there's AAS. To start, ASA, given two triangles, triangle ABC and triangle DEF as pictured, with angle A congruent to angle D, AC congruent to DF, and then angle C congruent to angle F, we want to prove that these two triangles are congruent. Okay, in order to do that, what we're going to do is first just mark off our triangles, right? So we have what I have drawn up on the triangles. And before we really dive in, I want to recall axiom C4. Now, axiom C4 says that given angle BAC and a given ray DF, there exists a unique ray DE on a given side of the line DF such that angle BAC is congruent to angle EDF. Basically, all that's saying is that given some angle and another ray somewhere else, we can replicate that original angle. Okay, and the important thing here is the unique part. So this unique part is going to come in handy very quickly. Okay, so in order to prove ASA, there's kind of two different cases, and the first one's really easy. Okay, the first one is we're just going to assume that AB is congruent to DE. So we are going to assume that these segments are congruent to one another. And that makes this really easy. So as you can see, we have SAS. We have that triangle ABC congruent to triangle DEF. And the other side is actually two parts, but we can just do it in one. The other part is that we're going to assume that AB is actually longer than DE. And if that's the case, I'm going to do this in this pink. If that's the case, then there's some point, we're going to call this M, on AB, between AB, such that AM is congruent to DE. Right, and then we get this resulting triangle on the left. We're going to ignore those teal marks now. So now we have that triangle. Let's see. Well, I got to do this first. So then this side, AM is congruent to DE. And then we have that purple triangle is congruent to the triangle on the right. So then that means that triangle AMC is congruent to triangle DEF. Which also means, so this is the case by SAS. And this also means that the corresponding parts are congruent, which means that angle MCA is congruent to angle EFD. This is a contradiction, because we already stated that angle F is congruent to angle C. And unless CM is the same as angle unless CM is the same as CB, so they're the same thing, then angle MCA cannot be equal to angle BCA because of this uniqueness statement right here. So because this is a contradiction, that means then that these two triangles are congruent by SAS. So triangle ABC congruent to triangle DEF. I just want to make sure I did that right. So that's definitely a contradiction. So I needed to explain one thing. In this case, we are assuming those two triangles are not congruent. And that's getting really messy. But that was the original assumption, right? So the first assumption in the first case, we're just going to assume that AB is congruent to DE. Then we have SAS, then the triangles are congruent, no problem. In part two, we are actually assuming that they are not congruent. And we're going to assume that AB is greater than DE, which means there's a point M on AB such that AM is congruent to DE, but then that leads to a contradiction because angle C is congruent to angle F, not angle MCA is congruent to F. Therefore, the triangles are congruent and all is well. Okay, a small word before I move on. Technically, we would have to do AB is also less than DE, but all we're really doing is we're swapping these two triangles around and everything else is the same. So without loss of generality, the same thing happens, just with letters swapped. Okay, and that's the proof for ASA. And we're going to get a really similar case for AAS right? So given two triangles, triangle ABC and triangle DEF, with angle A congruent to angle D, angle C congruent to angle F, and line BC congruent to line EF, when we want to prove that these two triangles are congruent. Okay, so like I did before, everything that we are given is marked, right? So angle A congruent to angle D, angle C congruent to angle F, and BC congruent to EF. And again, there's two cases. In this case, though, we are focusing on this middle segment, right? So the goal in all of these is really to try and get to SAS, which then proves it for us, right? So in this case, what we're going to do is we are going to just assume that AC is congruent to DF. This leads us to SAS, right? AC congruent to DF, C congruent to F, and EF congruent to BC. And then we're done. And then this means that triangle ABC congruent to triangle DEF, and our statement is true. The other way we could do this is let them not be equal. Okay, so we're going to assume this isn't the case, and we're going to try and prove something else. And then hopefully we get a contradiction, right? So now we're going to get a picture a whole lot like the one above, right? So let's assume that AC is greater than DF, which means that there is some point on AC, which we will call M. And then we get that resulting triangle such that, so then there exists an M on AC such that AM is congruent to DF. So then this is congruent to this. And then we have that these two triangles are congruent by SAS again. Is that right? No, I want to do this a little bit different. We're going to say that M is over here. And we're going to draw this. And we're going to assume this. That makes things a lot easier. So such that MC is congruent to DF. Then, again, as you can see, triangle BMC, I guess MCB, MBC, we'll go with MBC, is congruent to triangle DEF. By SAS. And then by SAS, the corresponding parts are congruent, specifically angle BMC is congruent to angle D, which can't be the case, right? Again, because of that uniqueness statement up top. So this draws a contradiction. Because ray AB is not the same as, is not distinct from, is distinct from angle, from ray MB, right? So ray AB is not the same, so is distinct from and then it breaks our congruence statement 4, and then we have a contradiction. Therefore, the triangles must be congruent. Oops. And then that's proven. right? So we proved angle side angle, we proved angle angle side, and again, it's really relying on this C4 axiom of uniqueness. And then we also proved that every segment will have a bisector. Okay, so thank you for watching. I hope all is well.